Welcome to the video presentation of BANet, Bidirectional Aggregation Network with Occlusion handling for Panoptic segmentation. Panoptic segmentation is a unified task of semantic segmentation and instance segmentation. One key issue for the unified task is how we model the connection between the two subtasks. We've noticed that they are complementary with regard to features. For one thing, semantic segmentation provides contextual cues to enrich the features for instance segmentation. For another, instance segmentation gives the structural information on objects, which also enhances the features for semantic segmentation. Thus, we build a bidirectional feature path between the two subtasks. Another issue for panoptic segmentation is how we handle the overlapping objects. We propose a novel occlusion handler. Now let's walk through the whole pipeline. The input image goes through a vanilla backbone and an FPN to extract shared features. The multi-level outputs of the FPN are fed into the semantic head to obtain semantic features. The semantic to instance module takes the semantic features and the FPN features as input. For each instance, it applies the ROI-aligned operation both to the semantics features and to the FPN features, and uses the addition of them as instance features. Then, the instance features goes through a vanilla instance head to predict categories, bounding boxes, and masks. Meanwhile, the further processed instance features in instance head are fed into a novel operator ROI-inlay. ROI-inlay receives the instance features and recovers the spatial structures of them. Features of different instances are filled into an empty tensor. The instance to semantic module aggregates semantic features with the inlaid features by two submodules, namely SIM and OCM. SIM enhances object structure information. OCM provides actual global object layouts. The aggregated features are used to perform semantic segmentation. So far, we've finished the task of instance segmentation and semantic segmentation. To obtain the final panoptic segmentation results, the instance predictions are post-processed by an occlusion handler. Occluded regions are first located between several instances. In this case, there is an occlusion between a plate and a human. We compare the visual similarity of the occluded parts and the candidate instances. Eventually, the instance predictions are combined with semantic segmentation to obtain panoptic segmentation by simply prioritizing things over sub-regions. We train our models on COCO trainset and evaluate it on well and test depth. The left pictures gives performance of ResNet 50 FPN-based models. The DAG symbol indicates whether deformable convolutions are used. Our model surpasses previous methods under the same circumstances. The right picture shows results on COCO test depth. Our model outperforms UPSNet by 0.7 percentage points under the same training setting. Here are some examples of our model's output. The dotted boxes highlight the regions that are greatly improved after adding our proposed modules. As one can see, adding bidirectional segmentation makes the sub-regions more stable and refined. Nevertheless, we noticed that there were some typical bad cases. The first one is due to the instant insensitive mask head. When a box contains another instance of the same category, the regions belongs to another instance is misactivated. This leads to the phenomenon we call fake occlusion, hurting both SQ and RQ greatly. The second type is what we call single instance multiple detections. Current two-stage methods apply class agnostic MMS to eliminate duplicate predictions and treats each left box as an individual instance. This strong hypothesis can do great harm to RQ. A further merging step is necessary.